specifically focus on this framework called noisy quantum trees. They're essentially a way of dealing with noise for protecting quantum information from noise and how to retrieve them. So we'll talk more about that. And that will be the main focus of this talk. If time permits, there's another topic that I want to talk about, which is how do you distill pure states from noisy states? Specifically, how do you distill pure bosonic states from thermal bosonic states, specifically coherent states? So if time permits, I will get to that. But the main focus of this talk will be about noisy quantum trees. Okay, so let's get into that. So this is the title of our paper, Noisy Quantum Trees, Infinite Protection Without Correction. We'll explain why we use that phrase. This is the preprint. It was accepted to NPJ Quantum Information and should be out soon. So yeah, let me start. So we'll start with the task that we all know and love, which is we want to protect quantum information indefinitely, given noise at every time step, right? This is sort of the basic assumption we always make. But I'm going to add a funny assumption to it, funny restriction, that we have access to a stream of fresh ancilla, low entropy qubits, but we're not allowed to perform any error correction. And we're not allowed to perform any error correction. Given this, is it possible to protect quantum information indefinitely? Right? That's the question. So a model that exemplifies these assumptions is a noisy quantum tree. So you have some information in the state size, if you could consider it to be a qubit. So you have some root data qubit of this tree, and then you unitarily interact it with fresh ancilla. Right? So in this case, you're interacting with a single ancilla, but in principle, you could interact with as many ancilla as you want. And the children of this process now suffer independent local single qubit noise. Right? So we said there is noise at every time step, and that's the presence of these local independent single qubit noises. And this repeats. So this essentially produces a tree. As you can see, the only thing that we are doing here is we are interacting our information that is within our tree to fresh ancilla to add more branches to our tree. We are never doing any form of error correction before. So just to clarify what we said, in the standard setup of fault tolerance, we are allowed all sorts of tricks. We are allowed encoders, measurements, classical communication, decoders, and these can happen at any point in the circuit. You can do them anywhere mid-circuit in some large computation. But what you're not guaranteed is that these things are actually noiseless. Either the ancilla that you add are noiseless or the gates that you add are noiseless. You don't have any of those guarantees. Whereas in noisy quantum trees in our setup, the resources that you are given are your ancillas are noiseless. These encoders, these unitaries that we have used are noiseless. You can implement them perfectly. You can do some noiseless decoding at the very end of the tree. You can't do anything at the very start. So all the information is being protected within the tree. And at the very end, you can do some decoding. But what you're not allowed, as I mentioned, is any measurements, classical communication, or error correction mid-circuit. Right? So you're not allowed any of those. Right? So in this model, as I mentioned, you have a single qubit of information that is being delocalized, but it's being delocalized in a noisy way. Now, in this model, even though it seems like just a random network I drew, this is a very natural model for noise in encoders of concatenated codes. So if I just remove this noise, this would be a concatenated code. If these were specific encoders for some stabilizer code, you could also use this as a model for dispersion of information through some cold, rare environment where you have some noise every time your dispersion process, where the dispersion process is modeled by this unitary, right? But even before we start, the question is, if I keep doing this ad infinitum, is infinite protection even possible in such trees? That is, do the leaves of this tree remember anything about the root that was sent in, given some non-zero amount of noise? Right? Is this even in principle possible? So this question has precedent even in the classical situation. And there's this notion of a classical tree. Classical tree is much simpler. In some cases, it's a special case of a noisy quantum tree, where each node is just a copier. You can think of it as a repetition code. So you copy your bit from 1 to b bits, where b is called the branching number of your tree. In this case, b would be true. And on each edge, you have a bit flip error with some probability P. And a setup like this has, again, broad applications, even in classical literature, for instance, in Ising models in statistical physics, or ancestral reconstruction in biology, in genetics, so on and so forth. And you could just look at an example here where, let's say I sent the bit 0, it copies into 0 and 0, and some noise process that you don't have access to, let's say the bit flip happens here, the 0 becomes a 1, and then you continue this game to the very bottom. So if there was no noise, this would have been all zeros, but because there is some noise that was sampled in this process, some of them get flipped to ones. And that's the noise that you see. So the question is, can I look, in the classical case, can I look at this bit string at the bottom and infer what the root was, right? That's the question. Now, there are lots of reconstruction algorithms you can consider. You can, for instance, consider the naive full majority voting, where I just look at the most common bit here and guess that to be the bit on the top. But that is not very good because you don't consider the structure of the tree. So you could do something that sort of has blocks and considers the structure of the tree and improve those algorithms, so on and so forth. But in general, the question there would be, how well can you infer in general? And is there a noise threshold? Because that inference could depend on knowing the noise rates within the tree, right? And it turns out the answer to that can be quantified, for instance, using the total variation distance between the probability distribution over bit strings at the leaves given input 0 or given input 1. Right? So those are those two conditional probability distributions, and you would consider their total variation distance. And because the total variation distance is a proxy for the highest probability with which you can distinguish those two distributions, it tells you how much information about the input bit was transferred to some level T in this thing. So the T there is the depth of your tree. Yeah, please.
Maybe very naively, like, can you do better than full majority of component? Like,
yes, you can. So you can do better than full majority, but there's a small caveat here which I'll mention in a second. So what it turns out is that in the infinite depth, there is a critical noise threshold, and the critical noise threshold, which depends on 1 over the square root of the branching number of your tree. So for instance, for this tree where b is equal to 2, that number is around 14%. So when your error is smaller than that critical threshold, some information about your input bits always persists to infinite depth in your tree. So you're taking the limit where t goes to infinity. Right? It's always strictly greater than 0. Whereas when the error is greater than that, the error rates within the tree are greater than that critical noise threshold, there's an exponential decay of information. So in the infinite depth, all information about your root is lost. So there are no correlations between the leaves here and the root that was sent. So there is a coding phase and a non-coding phase that exists. And this was actually found rather recently in like 2000. Even though this question was asked in the 70s and 80s as well, right? It turns out that actually strategy, as you asked, that recovers this noise threshold asymptotically is just majority voting in the limit. It actually recovers. So majority voting actually recovers the same limit in the infinite, recovers the same threshold in the infinite limit, even though its performance for any finite t is not optimal. So it recovers the same threshold, but it's not optimal for any finite. Right. Okay. So that's a small caveat there. So given this, we can sort of harp on this intuition where, okay, so instead of having a copier there, which was the repetition code on every node of my tree, I can replace it with for instance, a unitary. And the intuition from error correction is that by delocalizing information, you can protect against local errors, right? So using that intuition, we can essentially say that, of course, there's information decay due to noise, but we should expect some protection of information due to delocalization, right? So we have these two competing effects, and we can sort of cast the earlier question, which was about classical trees, as we were getting protection by copying, sort of a repetition code, and then there's errors, which are anyway decaying your information. So you have these two things. And the question is there, in the limit, does one always win, or is there some regime or some phase changes that happen in this process? And let's consider So to operationalize this question, we can say specifically we pick some set of unitaries in my tree and some set of noise channels, and given access to all these, given access to all the leaves, is there some way to recover, at least approximately, the root for a finite or infinite tree? And specifically in the infinite tree, does there exist a non-trivial noise threshold in terms of the noise parameters of these noise channels for recovery of this infinite tree? Right? And you just want to do it approximately, because in principle, I could lose all my information and no recovery could be possible for my input state. Right? The question is, even is approximate possible in the infinite depth limit? So to do this, let's consider a simple example. So Michael is aware of this example. So we call this the bell tree. Bell tree is a binary tree, and it's called the bell tree because this encoder is just the encoder to the bell state. So given some input in the computational basis, I output one of the two bell states, two of the four possible bell states. So we call that a bell encoder. And the noise again is really simple. It's just independent bit flip and phase flip noises, errors on each part. So now let's have some quick remarks about this bell tree. We call it a very simple example, and it's sort of in some sense the most non-trivial quantum example going from the classical case, because it's just a classical tree, right? If I didn't have that Hadamard, it's just a classical tree, which is the C naught is just copying information. But I've had a Hadamard on each edge, right? So that's the first. Second, now this is a very important point, which is the bell encoder as a code, as an encoder to a stabilizer code, realizes the same code space as a copier. The presence of this Hadamard within this encoder doesn't change my code space. It has the same stabilizers. So it turns out, but clear, so even though the classical tree has, the encoder to the classical tree has the same code as the bell encoder, clearly the classical tree does not give you any protection against phase errors, because it's only a C naught. It doesn't give you any protection against phase errors, as I will specify more clearly later. But the bell encoder actually does give you protection against phase errors as well, just like it gives against bit flip errors. So for these trees, it's not just the code that characterizes their performance, their behavior, but rather the exact encoder that you choose for your code actually starts mattering. Right? So normally in error correction, we can just abstract out and think about the code space. In the context of this, you can't do that. You actually have to care about the actual encoder and the dynamics of that encoder. And thirdly, I sort of harped about this intuition that error correction, that there's this protection that you get from error correction. As an encoder, this is a very bad encoder. This is, in some sense, distance 1, which means it can't even detect generic single qubit errors. Forget correcting them. So why, you shouldn't even, this doesn't even give you protection. But it turns out even this minimal model of a tree can protect information to infinite depth, even given non-zero amounts of noise within the bulk of the tree, right? So let's understand this plot. So the x-axis is the physical error rate within the tree. So that's the error rate within these boxes. For simplicity, we assume that the bit flip and phase flip error rates are the same. So that's just the x-axis. And the y-axis is the logical error of the entire tree. So it could be the finite tree or the infinite tree in the limit of the infinite tree. And because this is a concatenated code, it makes sense to talk about the logical error. So here we are focusing about the logical x error. So when the logical x error goes up to 1 over 2, that means that it's a uniform bit flip channel. The entire process on a single qubit of logical information is a uniform bit flip channel. So any information encoded on the computational basis is fully lost. Right? That's what this would mean. What you see is clearly when the noise is large enough, the error does go to 1 over 2. So you lose all information. But the important thing is that there is a regime, for instance, to the line here, right, to the left of this 0.5% line, when the physical error rate within the tree, all through the bulk, is smaller than 0.5%, there is some in the total logical error does not go to 1 over 2, but is rather strictly less than that. That means that some information encoded in the computational basis in the root of my tree does actually get transmitted to infinite depth. right? That actually get transmitted to infinite depth. Right, so there's a clear exists. So this proves the clear existence of a non-trivial noise threshold for this tree, right? And there are some other lines, for instance, the line on the right shows an upper bound for my noise threshold, which is beyond this 8% error rate. We've proven that there's an exponential decay of information. And that 8% actually comes from an interesting number that I'll talk about later. Because there's an exponential decay of information to infinite depth, clearly no information is preserved, or in other words, the effective channel, the logical channel, becomes a uniform bit flip channel, and thus all information is lost. Right. So clearly between these two numbers, the actual threshold is somewhere in between. But the more important thing here is that there is clearly the existence of this coding phase or this non-trivial noise threshold. Right. We prove these three lines. I've done three. I'll mention the third one. We show the existence of this non-trivial noise threshold by actually constructing a decoder for this bell tree. So we'll talk more about this recursive decoder. The upper bound comes from this information theoretic bound that shows the decay of information, or specifically correlations between the root and the leaves, and how we can borrow classical results for proving that for this quantum case. And then finally, there is a more general numerical recipe, which is this general belief propagation decoding algorithm for concatenated codes that you can apply to any finite tree. So we do some rudimentary numerics on that and get this slightly improved curve that says that the bound is somewhere between these two lines. And at some point, I'll mention Michael's work also related to this, and where they have improved these numerics, and we get much tighter bounds closer to this thing. Yeah.
Maybe for the recursive decoder, it might appear as if there's a vertical jump. Like, is that a real some kind of first order transition, or this is just like the result of numerics? Like
That's a good question. I think the short answer is I don't know. I think it's more a feature of numerics at this point. Can't say for sure. I don't know actually. That's a good question. Okay, so let's go to the. So first, I'm sorry. So let's first talk about the recursive decoder. So the recursive decoder is called recursive because, as mentioned, sort of just to again belabor this point, in usual error correction, you're sort of patrolling your system. You're looking as errors build up, you correct them as they build up, and you remove entropy from the system. And you ensure to get general fault tolerance, you remove errors faster than they actually accumulate. This is more like a detective strategy. Sort of the damage is already done in your tree, and now you want to sort of recover the state. So you assume that the decoding that you have is noiseless, and here you're allowed to do whatever tricks. You can do something global, you can do something local, you can do whatever you want. But what you have, the state that you've given here is something that has already suffered noise fully. But you have these exponentially many leaves that are all noisy, and you want to recover the root. So in principle, I could have a large global strategy, but we call it recursive decoding because we actually do only small local strategies of recovering in these local patches. So we look at pairs of these qubits. So specifically, you see each decoder, so we call it it's a novel decoder in the sense that we came up with it. It first augments each qubit with a pair of classical bits. We call them reliability bits. So we associate each qubit with a reliability bit, and the decoder acts on two qubits along with its reliability bit pairs, and the output is again a single qubit with one reliability bit pair. Right? So you see every qubit in this decoding process now has these two bits. Initially, you can just set these reliability bits to all be 0, but later you will see I will start updating them as the decoding goes forward. So now this is recursive and it's recursive in the sense that we never act on the whole children together. We only act on blocks of 2. So here I'm only looking at depth 2, but in principle I could look at something larger. So if I, for instance, look at 4 levels, this is the structure. Again, as I said, in principle I could look at a large unitary that does some joint operation on all these leaves, but I'm only looking at pairs of these at any given point in time. So now let's run through how this decoding works. First, again, some quick comments on the Bell encoder. As I said, it cannot even detect single qubit, generic single qubit errors. That's kind of half a lie because it is distance 2 for X errors, which in other words means that it has a stabilizer ZZ, so it can detect single qubit X errors. Furthermore, it can actually correct a single qubit X error if it knows where it happened. Right? If you know that there's an X error that was detected and one of the two qubits had happened, you can correct that qubit. Right? But if I just done that thing, there's not enough information in just one round to allow me to do that. So what we do is now we use these reliability bits to sort of supplement some additional information about location. So the way that we do that is I don't expect you to sort of understand what's happening here, but sort of the thing that you should take home from these two things is that each of these decoders have a way of decoding that is informed by these reliability bits. And additionally, in every round, based on the syndrome that you observe, so that's a syndrome measurement that you observe, that is whether an error was detected or not, you update these reliability bit pairs in some appropriate way and output a single pair. Right, so that's the thing. But I'll give you a much more intuitive explanation of what's happening. So the way that you want to understand it is first, again, remember that for this Bell encoder, it has a single stabilizer, which is just ZZ. So in the first round, it's clearly sensitive to X errors. But then in the subsequent round, because of the presence of that Hadamard, we always add a Hadamard to all my qubits at the end of every round, as you can see there. So given that, all the X errors become Z errors and all the Z errors become X errors. So consequently, in the second round, you're only sensitive to what are erstwhile Z errors, because at this point they've become X errors. Earlier there were Z errors. So in the first round, you were sensitive to X errors, and in the next round, you are sensitive to the erstwhile Z errors. And then again, the subsequent third round, you're again sensitive to X errors, right? So going back, so in round 1, you're sensitive to X errors. In round 3, you're sensitive to X errors. So in all the odd layers, you're sensitive to X errors, whereas in all the even layers, you're sensitive to erstwhile Z errors, right? So now let's just focus on how do we deal with the X errors. So now this is just sort of a simulation, sort of a dry run to give you a sense of what's happening. Let's say when I'm doing the first round of decoding, I detect an X error here and an X error here. I just detect one. I can't really do anything because I don't know which qubit caused me that error. I can't really correct it. So what I'm going to do, whatever errors happen in this light cone, in this part, all get funneled to this qubit, right? And whatever errors happen here, all get funneled to this qubit. So I will flag this qubit, which will start playing a role in round 3, not right now. So I'll flag this qubit and I'll flag this qubit. The way I flag it is just with a bit. I just turn from a bit 0 to 1 and send it to that round to keep track of this. So now once we go to round 3, let's say it so happens that an X error is detected here, but nothing is detected here. There's no X error detected. Now let's think about what's happening here. There are two things. First, an error was detected, as I said, but the left reliability bit was also flagged. So now you have a distance 2 code with an error detected, but with some locational bias information. So given that you know this location, you correct it. You correct that. Here we have not detected the error. We just know something was unreliable, so we just don't do anything. We just decode as it is. In the sense, we just apply the inverse unitary. Don't do anything. No correction. So no updates there. And that's the trick. That's all the decoder does. And you just keep going on. I'm sorry. Now for erstwhile to handle Z errors, we would do the same, but in the even levels, with a different set of reliability bits. Right? That's why we had a bit pair. There's one set of bits that was handling all the odd layers and one bit that was handling all the even layers. We have these two bits that we are streaming down our decoder. And that allows us to handle both the X errors and the Z errors. Another way of thinking about the effect of this Hadamard that we did that sort of changed X to Z was in one round, the effective stabilizer you're applying is ZZ, but on all the odd rounds, the effective stabilizer you're applying is ZZ, but on all the even rounds, the effective stabilizer you're applying is XX, right? So one time you're sensitive to X errors, another time you're sensitive to Z errors. So you can handle both of them. And some sort of highlights of this decoder is that first, it's very easy to implement because you're only applying things locally. The overhead is only classical bits. It's very easy to analyze numerically. So for a nice symmetric tree, you can just, and it just scales with the depth. It's very easy to analyze numerically. It's very easy to also analyze analytically, which we did in our paper. And it turns out to be nearly optimal, right? In the regime that you actually care about, it's nearly optimal. So we'll see so to justify these, let's just talk about the, the performance. So what we looked at before is a decoder with depth 4, but in principle, you could analyze any depth. So here we numerically analyze to different levels where the x-axis is the number of levels. And each of these lines is different amounts, is the error rate within the bulk of the tree. So you have starting from 0.2% up to 0.8%. And you see that there's a transition happening at 0.5%. So when you're below 0.5%, obviously your error increases with the depth because the error happening through the bulk. There's a larger part of the bulk that's being considered. But it doesn't go up to 1/2. It sort of saturates down and it stays at some value that's strictly less than 1/2. So you see that you don't lose total information as you go to infinite. As you go to infinite depth, you see the saturation. But once you are above 0.5%, you see that your noise sort of diverges and you lose all information. So you have a clear separation of a coding phase for this recovery that's here and a non-coding phase when you're above it. See this clear separation. And you see all this dynamics by just analyzing this rather simple decoder. So that 0.5% line was the same line that I showed earlier. And we have an analytical proof. So our analytical proof is not very sophisticated. We make some simplifications. So we get a lower bound for this number around 0.25%. But the important thing is that we have an analytical, so rather than just this numerical thing, we have this analytical proof that there exists this coding phase. It shouldn't be very hard for us to have improved our analytical analysis and gotten this line closer to this. There's only so much time. Oh, sorry. How do I? Yeah. And then finally, you can compare the performance of this decoder with with sort of this global optimal decoder. So this whole tree is just a large concatenated code, and you can apply this already well-known optimal and efficient decoding on concatenated codes from David Ponoff from 2006, where you apply this belief propagation algorithm on the syndrome data, and but you sort of hit these exponential overheads, and we didn't have very sophisticated numerics for this, so we only analyzed it for up to 20 levels. But you already see that this gives you this different curve. So what you'll see is that as you increase the number of levels, this line, which is orange, starts shifting closer and closer to this blue line. And this is what I meant by saying it's nearly optimal. Whatever the infinite tree is, the infinite tree would sort of lie between these two, this orange line and this blue line. So it would be something like this. But you already see that within the coding regime, which is below the threshold, the performance of this thing is almost the same. It's off by some 10% or 20%. So it's nearly, it gets the right order of magnitude. It's nearly optimal. And if we actually, so we've not done this, but like for instance, Michael has much, Michael's work with Grace Sommers and David Hughes. They have a much better line where it comes much closer to this, and you start seeing that this gap is actually very small. So the interesting thing here is that our decoder, even though it's pretty like, hacky and not very sophisticated and stuff like that, it manages to do remarkably well. And we are not very sure why, and that's something that is still left. Because it's very simple. It manages to do extremely well, very close to what is otherwise sort of this, exponentially hard global search, right? It's managing to do really, really well. So that's an open question for us as well. So yeah, so this is the thing that I mentioned, where this is a paper with by Gray Summers, David Hughes, and Michael, where they again look at the bell tree, and you see that this is the equivalent of this plot, but instead of looking at this recursive decoder, you're looking at sort of this optimal decoder that's doing the belief propagation thing. And for like, instead of looking at, we look at that for only 20 levels, they look at it at like 160 levels. So they have a much.
Yeah, we don't have the decoder, we have the statistical mechanics mapping that lets us study the decoder. I guess that's the.
I think that's, yeah, so there's this detail about how you do some Monte Carlo on that.
Well, we don't actually keep track of the disorder.
I see.
The averaging as you go up the levels. The algorithm is like linear in T, or it's like polynomial in tau.
I see. Okay, so I have questions on that we can discuss about.
It comes from the spin glass.
I see. So that's interesting. So we need to understand that better. So that's a thing that we should talk about. So they analyze that, and then they see that they sort of improve that estimate for the threshold that's closer to 0.6%. So that's very interesting, because the threshold that our decoder gave was 0.5, around 0.5%, and the threshold that you guys are getting from your thing around 0.6%. So in some sense, the bell tree kind of seems to,
But there could be a small.
Yeah, absolutely. We don't expect that our decoder is perfect. So there should be a small gap, but right now the gap is already very small. Right, that's the interesting thing, right? Like, when we started, we just had these two lines. It's 8% and this 0.5%.
Yeah, Grace is amazing with these numerics.
Yeah, so we should discuss more about this, like these numerics, and also sort of this number that we have is when we started, we thought it was pretty rudimentary, but there should be this. The fact that it's coming to something that's pretty close to what you get with all these rather robust numerics is interesting, and should understand that better. Okay, so we spoke about this line and this line. So now let's finally talk about this line with this upper bound, which is again interesting because it sort of again talks about this general framework of trying to upper bound trees. And a lot of these tricks you will see should be possible to extend to other sorts of network architectures, because they just sort of work on general properties of Clifford unitaries and the Pauli group. Okay, so how do we think about this exponential decay? The quantity that we care about is we compare the tree. So this is E sub t is a tree of depth t, okay, noisy tree of depth t, and we compare it with the same tree that has been precomposed with a uniform bit flip channel. So why would we do that? This is a channel that does not transmit any information on the computational basis, right? So if we consider the diamond norm between these two channels, if the diamond norm between them approaches 0, that means that the tree channel that we are considering, the noisy tree channel that we're considering, is approaching another channel that does not transmit any information in the computational basis. So if I can prove, sort of the name of the game now is find some upper bound that as t goes to infinity, goes to 0, right? So if that bound goes to 0, that means that this number approaches 0. And as this number approaches 0, you can get some regime where, so in those regimes of the noise parameter, it turns out that your tree is not transmitting any X basis information. And you could play the same game with, for instance, the dephasing channel, and now you can conclude things about information in the X basis, right? So you could play this game. So we have some time, so I will indulge myself and give a sense of what the proof does. So with the way that the proof works is by first noticing that just using the definition of this uniform bit flip channel, this is just algebraically equivalent to that up to a factor of half, where instead of precomposing with a uniform bit flip channel, you're precomposing with a X unitary, right? That's the X unitary. Now, all these encoders in my bell tree, or more generally in like these Clifford encoders, are they're Clifford clearly. So I can sort of take Pauli noise and commute it through to create correlated Pauli noise. So what I have here is just my noiseless tree, so just the encoder, followed by some large correlated Pauli noise at the level T. So I've sort of commuted all my noise down to my tree, down to the leaves. And here, the difference is I've just added the effect of a logical X. So logical X would be some large unitary that acts on all the leaves. So that's this. So the effect of this is equivalent to the effect of this, right? And then I can sort of just use data processing inequality to sort of drop off the isometry, which is the encoder, and that gives me that upper bound. Okay, so first, have weakened my statement by using that upper bound. Now let's focus on the effect of this logical X. The effect of this logical X obviously depends on what set of logical operators you pick. But you can pick a specific set, and that realizes a logical subtree, where you can look at X. In the next round, the effect of X at the root is equivalent to the effect of a single Z for the bell encoder on the next level. And the effect of the Z in the next level is equivalent to 2 X's. And you can just continue, and you can sort of highlight a specific logical subtree for instance, for this bell tree. And then we do this sort of pruning of our tree, where we sort of drop certain noises in our tree. So now we're looking at a tree that's slightly less noisy. We only keep noises that are compatible with the logical subtree. So each of these logical subtree, here your logical operator is X, here your logical operator is IZ, here your logical operator is IIXX. So in each of these lines, we only keep the bit flip noise. Here we keep only the phase flip noise. We drop those things. So we're considering a slightly less noisy tree. Okay, that's all right. But that we're only looking at upper bound, so we get a weaker upper bound now. Now let's focus on this noise. So now this noise, as I said, for any level T is this large correlated Pauli noise. So it's some Pauli operator times the probability with which that Pauli string has been sampled. And it turns out that the diamond norm distance between two Pauli channels is just the total variation distance between the probability distributions for sampling those Pauli strings. So that's just a hard equality. Finally, because once we pick this logical subtree, information regarding this X at the root is only limited to within this logical subtree. So the bits here are fully uncorrelated with the bits here. So you can the total variation distance between these two classical distributions can be fully restricted to only looking within the logical subtree. And within this logical subtree, just the way it's defined by this logical effect. So within the logical subtree, the logical effect is just sort of complementing it, adding that one. So now you have a distribution and its complement, but now you're looking at a tree which is sort of the subtree of this larger tree. So even though this is a binary tree, this is a much smaller tree within that tree. And this is exactly the classical problem. This is exactly the classical problem that was resolved by Evans et al. In 2000. And now we can apply the classical results to this logical subtree and ask, okay, what's the branching number of this tree? It turns out there's a general notion of branching number where you have an irregular tree. And this notion of branching number, it turns out, would be, for instance, the geometric mean of 1 and 2. Because in one round it's 1, the other round it's 2, one round it's 1, 2. So it would be the geometric mean of the two. So it will be square root of 2. And now we saw this critical noise threshold in the classical result. Above this number, you have an exponential decay of information. So in place of B, you substitute square root 2, and that gives you this number, which is the same.
Guess it makes sense, at least heuristically, why this would be a weaker upper bound, because the logical actually can live like in many.
Yes,
different-
exactly. But also there's another thing, which is that to actually do this analysis, we dropped a bunch of noises, right? If you actually go through the details, we only considered noise that is compatible with the logical subtree. So we were considering a less noisy tree. So there are lots, and then for instance, in this step, there's another important thing here. For instance, if you take this step here, the diamond norm is a maximization. So instead of optimizing within the code space, you're optimizing over all states. So that's another. So there are lots of places where you sort of weaken this bound, but end of the day, you do get a bound, and that was interesting. So that gives you that interesting number 8%. And there's a lot of freedom again in this bound in the sense that it depends on the logical subtree that you picked. The place where this becomes important, as you will see, I'll mention it, is where you can actually show that it's not possible if there exists any logical subtree that does not grow exponentially. You know that your bound goes to 0, right? So you will see why. I'll show the exact expression and it will become very clear. But you can, for instance, you can sort of have a characterization that it's sufficient if you can just show that there is one logical subtree that does not grow like a tree, that grows sub-exponentially, you lose all information to get in depth. So that's sort of an interesting result there. So we'll talk about that. So this was all about the Bell tree. Obviously, we don't prove Bell trees are pedagogical example. We prove for general stabilizer trees. So we look at general trees where the encoder U is a Clifford encoder, and there is Pauli noise on each of the edges. And there's always this generic behavior where there is a regime where you can prove analytically that there is that it's strictly less than 1/2, right? So there's a clear coding phase. And then there's an exponential decay for some regime that's greater than sort of depends on, for instance, the branching number of your logical subtree. So you have a clear non-coding phase and a coding phase and some transition in between that we have not fully characterized for the general case. But in the Bell tree, we have slightly more control because it's a specific example. So again, as I said, there's a general threshold theorem for stabilizer trees. So there's a non-zero noise threshold for all trees that have encoders whose distance is 2 or greater. And even for some distance 1 examples, for instance, like the Bell tree, you can show that there is a non-zero threshold. Okay. Then there's this exponential decay. So this is the term that I was mentioning, that there are two competing terms. There's one with as depth grows, this decays exponentially. This is the error rate within my tree, within the bulk. And this number obviously decays exponentially. But the other counter effect here is what is the weight of the logical operators, or in some sense, how many branches does your logical subtree have? So if you can show that so now this bound is true for any logical subtree. So for any given encoder, there is some arbitrariness in the logical operators you pick. Thus, there's arbitrariness in the logical subtree you pick. But if you can find a single logical subtree that grows sub-exponentially, you already know that no information passes to infinite with that encoder.
So I guess you have proofs that for the Bell tree, all subtrees are.
Yes. So yeah, we have an argument that this is the minimal subtree that you can have. You can just look for something like a Bell tree. There are only like a finite number of combinations. There's 6, 8 or 16 combinations, and you can just check. Yeah.
Sorry, I think I got confused about something very basic. So, and the confusion is, why is this an upper bound for the diamond norm if you're restricting to a smaller set of like logical arrow on the subtrees? Like I would have thought this is a lower bound.
It's an upper bound in the sense that it's making the. So actually, that's interesting. So okay, so in that step, actually, it's an equality. Let me clarify that. So the fact that you can restrict only to something that is smaller is an equality. that doesn't weaken the bound.
Okay.
So that's yes. So if it did turn out at all, you
Oh.
couldn't, this was not an equality, then this proof wouldn't have gone through. This is actually a pretty, even though it seems trivial, it's a pretty critical step that this is an equality. Because normally when you drop information, it yeah. And yes. And then finally, yeah, you can obviously numerically analyze the exact threshold for any given concatenated code, and we do that for a few examples. For instance, the STEAN7 code and the Shore9 code. So that's it. So yeah, I don't know if I have time for the other stuff, but I will stop here and I'll go through questions. So the conclusion here is that we proved these new threshold theorems that show that infinite protection is indeed possible without error correction. So let's remember, we're not doing, so, this decoder was sort of a proxy for us to answer a more general question, that is there any information about your root left in these leaves? Right, that was the question that we were trying to ask. You would just ask that question sort of like a dispersal process, like, is there any information about my initial state? Does it remain in this noisy process? Right, and a proxy to that question, a way to answer that question is to see, okay, can I construct a decoder? Because if there is a decoder that can actually decode it, that means that some information obviously was left about the root, right? So we show that infinite protection is indeed possible without error correction by just delocalizing your information perpetually, even in the presence of noise. Information is protected to infinite depth. And sort of that upper bound already shows you that in this specific case, you actually do need this exponential bank of memory. You need to keep entangling to exponentially many things, because if your tree does not grow exponentially, that upper bound actually just quickly goes to zero exponentially, and then you sort of have lost all the information. So this exponential nature of spreading this information is important. And then this sort of provides a new perspective, because this sort of, as I mentioned, it's a simplified model for fault tolerance where you're focusing on only one of the resources that you have, which is sort of entangling to new ancilla. And the fact that you're just continuously entangling to fresh ancilla suffices to give you protection to infinite depth. Right, so your resources are ancilla rather than a specific measurements or decoders or syndromes. Right, so this gives you sort of a new perspective on the role of different resources in fault-tolerant protocols. I like this example because in 1996, when Peter Shor came up with his error correcting code, when people started thinking about the general theory of error correction, how do you say that? Harosh? Sergei Harosh? Is that how he says it? Serge Harosh. He wrote this article where he called error correction watchdog strategies. So the idea is you sort of watch the system for a bit as things accumulate, you like correct it immediately. They're sort of like policing the system, keep watching the system. This is more like detective work. So the damage is done, the murder is over, everything is done. Detective comes at the very end and you're like, okay, so now that the damage is done, let's look at what's possible and recover what the original state was, right? So quantum trees is more like detective work. So, so let's sort of some obvious future directions. One is obviously better estimates for the exact threshold for at least popular families of codes and encoders. Obviously, extending this framework to non-Clifford encoders, probably other things in the Clifford hierarchy where you have more control on how these things commute should be interesting. Random Clifford encoders is a very interesting thing where each of those unitaries are sampled randomly. We have some preliminary results, but nothing great because we just haven't had time. Other specialized noise models like coherent error. So erasure error, for instance, actually has already, Grayson has already had very interesting results on that. Another thing that I'm actually very interested in is, pragmatically, it doesn't seem reasonable that you have access to the entire sort of this exponentially large number of leaves. How much information can you get from just a small fraction of the leaves rather than all of them? Because using the structure of the tree, there are some intelligent and unintelligent choices for the choice of those leaves because of the structure of the tree. And then some of these techniques, some things we've not mentioned in the paper, but there are these there are other techniques that we have developed for like general arbitrary networks, but they're not very strong, so we didn't put them in the paper. But how do you generalize a lot of these methods to give useful results for general arbitrary networks is not just tree networks, is a general question. So yeah, I think I'll stop here. I don't want to go too long. But I have another part where I wanted to talk about distillation, but I don't think we have time for that. So
Yeah.
keep that off. Right.
You can give another seminar.
Yes, I can give another seminar later. You can always invite me again. But that's it. Thank you.
Questions? Just go on.
Yes. And yeah, people on Zoom.
Yeah, go ahead.
Usually you can go. Well, I guess at the beginning, I was a bit confused in the sense that at least at the formal level, I could always rewrite either a measurement or a dissipation channel in the form of like a bigger unitary acting on something else and your system, like just to kind of sense dilation. So, but I guess the point here is that like if you don't constrain the structure of the tree and what unitary and like what unitary you do and what fresh state you supply at all, then supposedly this would be a description that in principle also includes the standard formula of doing active correction, but maybe the point here is that we're considering very simple structure and very restricted set of operations, and the fact that it still has a threshold, that's the non-trivial part.
Yes, but also, for instance, I'm assuming that I have noiseless encoders. I'm assuming that I have noiseless decoders. These are not resources that I
Well, I think what she's saying is that there's these known results in fault tolerance that if you have fresh ancilla, you don't need the circuit measurements.
Yeah.
But the way those work is they basically turn the fresh ancilla into a classical computer.
I see. Okay.
That's obviously not what you're doing.
Yeah. That's clear.
I think that maybe there's a way to make it more precise, but I mean, basically you have no ancilla because the number of qubits you use is the number of states
Yes.
that are in the code.
Yes.
Maybe a more concrete question is, for example, are there constraints on the type of codes, for example, you can do this? Like you kind of talk about extension too, like.
So the framework by itself says unitary can be anything. Could be a code, it could not be a code, could be whatever. Can all, yeah, it's just like large concatenated code.
But the fact that you have a non-trivial threshold, like whenever you just have this binary tree, like you expect this to always work?
No, so there are examples, for instance, I don't know if I can go, I should have it in my, oh yeah.
You need the global distance to grow.
So in the paper, we have this things, for instance, I think this is the bell tree, but you could look at some small cousins, for instance, this doesn't work, this doesn't work.
Right.
So we have some partial characterization of that in the paper. Yeah. Yes,
about noise propagation or error propagation in your model as the fusion process.
Yes.
And is there, can I reconcile this framework with ideas like that?
We really want to. I don't know enough StatMech to do that. That's the only reason I've not been able to. Yeah. My belief is the answer is yes. So I just, but other than just hand waving and saying that, oh yeah, it's a model for diffusion, it looks like diffusion, I don't have good, accurate mathematical statements to make because I just don't know that field well enough.
Yeah, because part of the problem with these models is all of our numerical and analytical tools, they start from the leaves and they go down back to the root. You don't really have like dynamical pictures.
Yeah.
Where you go from the base.
Like sort of you can explore any amount of hardware.
That would be nice for the developer.
Thank you. Yes.
Like would it be possible to consider the case where like the size of the tree can either increase or decrease, like if you model the decoding step as part of this? So it probably can.
Oh, yeah, so that we did try. So that's actually something that we did try.
Okay.
Yeah, but in the sense that, we are making some additional assumptions about the decoder being noiseless, for instance. So there is a way of sort of, so yes, so what you said in principle can be done. We didn't really find it very useful.
Like when they have noise, I guess it's.
Yeah, even when it has noise, yeah, there are ways of doing it, but it turned out it wasn't very relevant to sort of the situations we were caring about, but in principle, yes, it can be done. So maybe for a different question, it can be a reasonable thing to ask. Yeah, I agree.
Well, yeah, let's thank Shiv again.
Thank you.
You stop the recording.
Yeah, once I figure out what to do it.